Hi, Kristian Krabbenhoft from Liverpool. From time to time I get questions regarding parameter studies and I'm going to go through a couple of different ways of doing that in OPTUM G2. So what I mean by parameter studies is you have a problem, for example a slope like this one here, and you want to calculate the factor of safety, but you want to do that not only for one friction angle but for a range of friction angles. And what you could do is, of course, you can then clone the stage and then you can use another material with another friction angle and then run the stages like that, record the results, and eventually plot up, say, the factor of safety versus the friction angle. So that's one way of doing it. A smarter way of doing it is, the slope I'm going to be looking at is this one here. It has a cohesion of 15 kPa and a friction angle of 25 degrees, a unit weight of 20 kilonewton per cubic meter. And the smart way of doing a parameter analysis where we would vary this friction angle from, say, something like, 10 degrees to 45 degrees is actually already described in the materials manual. I'll just bring it up here. It is under spatial variation of parameters, page 25. So this section of the manual describes how to use not only constant values of the parameters but also how to operate with, say, a linearly varying strength with depth profiles. So you could have something like this. So it's a bilinear in this case. Map, where you can input a whole map of parameters. So a two-dimensional map of parameters. And then there is something called multiple data sets as well on page 27 of the materials manual. And it's all described here actually how to work with not just one set of material data but multiple sets. And the way it works is as follows. So we have this, it's a little bit backward, but we need to use actually a profile. A profile defined by 2 points, say the top and bottom here, so -5 and 10, and then with the corresponding value being the same at top and bottom, meaning that we will have a profile with a constant value of the parameter in question, for example the friction angle. And we have the possibility here to enter one profile in, so I could say 10 at the top, and I say, let's say 25 degrees, and -5 and 25 degrees. And then you will see this change to profile, and I could do this run, and well, that's a factor of safety very close to 1 with this very coarse mesh of 100 lower bound elements. So it would definitely be more than 1 if you use more elements or an adaptivity and so on. If you check out the friction angle, that's just a constant, 25 to 25, top and bottom. Now what we can do is we can actually also load an input file, load a file with data. And so you want to go to import, and then you want to link to a data file. And this data file you would want to create. So I'm just going to go through the steps of how to do that. You first save the problem in a given folder, just so you know where you are. I have this one here that I'm working under, and I'm going to call that slope. Okay, so I then go to that folder. This one I don't need, and I create a Microsoft Excel worksheet. I can call that Phi. Open that up, and then I can create a profile here. So it was 10 at the top, minus 5 meters at the bottom, and then we can start entering our profile. So we can start with 10, 10. So if we just load this file, if we import just this file, well, we'll have the same as before, just with a constant friction angle of 10 degrees. But I can enter multiple columns here, so 15, and I think this is the way it works in Excel. I can extend this to, let's make it 45, and the same down here. So then what happens is that not just one run will be processed, but each of these columns will be processed in sequence. So first the first run is going to be with 10 degrees, then 15, 20, and so on, up to 45. Save that file, and then import it. P for parameter, profile, import, link to data file, and then you have various options with respect to it being single column data, multiple column data, or you can also have a custom range of data. But we're just going to select multiple column data here, and then select the file and proceed. And here is the link then, and you'll see the field up here changes to profile again. So if I then run this is just a detail I just wanted to be sort of open about. You're going to get an error, and there's going to be a message that this Excel file is being used by another process, so it can't be accessed. This is a Microsoft deficiency more than anything else. So what you have to do is actually close down this worksheet. You can close down Excel completely, and then it will run. So we then have multiple runs. We are determining factors of safety. Our best strength reduction factor is what is the result is recorded as, and this is a factor that of course increases as we go through the runs, because we start from 10 degrees, then 15, 20, and so on, up to 45 degrees. And that, of course, leads to an increase in the factor of safety. You can go into XY plots once you're done, and then plot the results here. So this graph here is the x-axis is the run number, basically, to which a friction angle is attached, and on the y-axis we have the factors of safety. Select the curve here and go to data, and then you can basically paste this data into Excel or some other program, and then plot it up as you wish. So that's the easy way to handle multiple material parameter data sets. What is a little less easy is suppose that we had a constant friction angle again of 25 degrees, and we wanted to vary the slope inclination angle. So say from 90 degrees to whatever, something down here. Again, we could create a sequence of stages and then manually change. In this case, it wouldn't be too onerous, but if more involved changes were required, this might be kind of a bit annoying to do. So there is another way around that, and that is to use the possibility of running OPTUM, the OPTUM calculation engine, through the command prompt. So if I type CMD here, and then I type OPTUM G2 CMD, then the usage becomes apparent. So you can call the OPTUM calculation engine in this way: OPTUM G2 CMD, then the name of an input file, and then an output file. That's optional. It's also optional to have a log file created, and this echo can be there or cannot be there. It just basically is a question of whether you want the progress dialog from the that you see when using the user interface. If you want the results there printed on the screen as the calculations progress. So this is one way of doing it, and it's also described in one of the manuals, the command line version. So there are some examples here. All the commands, of course, are described and explained, and some examples are provided. And what you can do if you want to basically process, if you want to do this type of analysis for a range of slope inclination angles, well, what you could do is you could generate a bunch of input files, and then you could process these through a batch file, right, and record the results, and then pick those up and manipulate them, display them as you like. So that's basically the same option that I'm going to be using here today, but in a sort of a slightly more automated manner through MATLAB, where I have set up a couple of functions that are useful for this purpose of basically conducting these types of parameter studies, or in general generating input files and then running them through MATLAB, picking up the results and displaying them, manipulating them within MATLAB. So the idea is basically have an input file, and then have a basic input file, and then on the basis of that base file, generate input files that are then sent to OPTUM G2, processed. The results are output to another file, and then those results are picked up. So the way it's going to work is that I need to create a base file, and that's pretty much this file I have here. I'm just going to rename it to slope. So I want to just maintain the original file here, slope base G2X. Let me just copy that. And then if I go to MATLAB, and I'm already in that folder, then I can open that input file up. And the input file, for those of you who have looked at it, you know it's in XML format. So it is readable, but it's quite a large file with lots of data, even for a very small problem like this. It contains basically all the standard materials, and everything you see on the screen is included in the input file. So even for a small problem, it's a relatively large file. And what we want to do basically is change this x coordinate down here, right? So we want to maintain a y. I should say this is at 0, 0, and so y equal to 10. That means this height is 10 meters, and so we want to basically change the x coordinate here to have a given slope inclination angle. So if I can find this entry for this coordinate, for this point here, the coordinates for this point in the input file, well, then I can change it manually, I can save the file, and then I can run it. Now, I can't find this manually. What I usually do to help me find it manually is to give it some sort of unique ID in terms of a unique number, so say 9.999, because I don't think the likelihood of that number being found anywhere else in the file is very high. And then I can take the file, I can search for this, and here it is. So that's node 7. And instead of changing, I could change it manually. I could change it to something like, say, 3. I save this, and if I then go into Optum and open it up again, well, you'll see it's changed. Instead, what I'm going to do now, I'm going to set things up to have this change be done in an automated manner. So I'm going to define a variable, and I'm going to enclose, I'm just going to call it x. I'm going to enclose it in dollar signs. That's totally optional. That's my own personal preference. I know there's no other dollar signs in the input file, so whatever I enclose in dollar signs is going to be a unique string. So I could then take this base file, I could then search for this, set up a MATLAB script to search for this string and replace it with another number, save the file under a new name probably, and then run the file. I could either open it manually as I've just shown, or I can run it through the OPTUM G2 CMD, and it's the latter option that I'm looking to exploit here in this little exercise. So I've set up a script, and I'll share a link to that script, a little MATLAB script, where I should also say, of course, now that I've modified this slope base file, right? So I have this quantity here, which to Optum is nonsense. Then it's not going to be able to read it. You're just going to get an error opening the input file. You just open the. That's why I wanted to keep just the very original file, so we can just have a look at that as well. But it's the base file here that I have modified. So the idea is, with this script, is have this base input file and then define what I call a run file. And the name of that is going to be the same as the input file, except this base is going to be changed to run. So basically define a run, the name of another file. Then there's a run command. That's eventually the command I want to be using in MATLAB to invoke the DOS prompt and invoke OPTUM G2 via the DOS prompt. So OPTUM G2 CMD, run file, the name of this run file, and then I'm creating a log file as well called logfile.m, and then echo, I've set that to on so we get results displayed on the screen. So the idea is take this base file, search for this variable $x$, replace it with a relevant number, create a new file, save the result as a new file, and then send that new file to OPTUM G2 CMD to be processed. So I have a list of variables. In this case, it's a very short list. It's only just one variable, and that's this $x$. The reason I use this struct, it's called in MATLAB curly brackets instead of regular brackets, is that I might have a list of variables. In this case, I only have one, but I might have a list of variables. I could have x and x2, and these variables could be of variable length. So then the normal standard arrays won't really cut it. I have to use something else, and this struct is appropriate for the purpose. You can do it in many other ways, but this thing works, and I've made quite good use of it. Now, I call this inclination angle, this angle here, to the horizontal, I call it beta. And I want that to vary from 10 degrees up to 90 degrees with an interval of 10 degrees. So I define this array called beta. And then I want to translate this angle into the coordinate up here. And since this is 0, 0, then the x-coordinate up here is related to the inclination angle in this way here. So x is equal to 10, which is the height, divided by tan beta. Remember the tan d, we're working in degrees here. So then I have an array of x coordinates generated. And then I basically loop over the entire array. It could be beta here, it could be x. And I have a MATLAB function that I'll share as well, which works in it's called Replace STR, replace string. And it works in the following way. It takes some string called old string and searches for that in a file called old file. Then once it's found, it replaces this old string by new string and saves the resulting file under the name specified here as new file. So in this case, the old string is this variable here, $x$. The new string is the entry in the array that we have generated of x coordinates. The old file is the say the base. I call this the input file. That's maybe a bit misleading, but the base file. And the new file is what I call the run file. So that's the file we actually run. And then I use this replace string to basically generate the new file. And then DOS, that's a MATLAB command. Run command, that is the command I want to be running, as explained before. As part of this run, a log file is going to be generated. And what is a log file? Well, that is a file that just contains the log, and the log is this thing here. So I'm going to have a file for each run that has this type of information. At the end of the file, there's going to be this string, best strength reduction factor, and then a number. So what I want to be doing is, after the run has completed, I want to read this log file. I want to search for this string, best strength reduction factor, and then I want to read off this number. And that is what this function here, another function that I'll share, does exactly. It searches for a string in a given file and then reads the number following that string. This number is recorded as res, and this number is entered into an array called fs, factor of safety. So that is how it works, and let's see if we can run this. So it's called, the script is called G2M_test. And so we start with a factor of safety of around 2, and then it decreases. Remember, we started from a slope inclination angle of 20 degrees, and then we increase it up to 90 degrees. So at some stage, yes, at some stage we fall below 1. This is entirely expected. And the output here on the screen, you can either keep that, that's what the echo command does, or you can get rid of it simply by deleting the echo command. So we are done now, and the results are recorded here in this array fs, and we can access that immediately, and we can also, we have the beta array. So here we have the inclination angle and the corresponding factor of safety. We can of course plot these, beta comma fs, and put some labels on if we want. So it looks like this. The inclination angle and the factor of safety for this very coarse mesh here, don't forget. So you'd really want to use more elements, use adaptivity and so on and so forth, probably upper and lower bound. The usual drill to eventually get something that is very close to the exact solution. And this is then how it looks. And we can not open the base file obviously anymore, because that contains still this variable $x$, but we can open the run file, and that has now terminated at or that has now reached, the latest run file has come to 90 degrees. You can of course save these run files under a different name corresponding to the properties, for example in this case corresponding to the slope inclination angle. So that's how that works. As I said, I will share this script, and I'll also share this this function, replace string, replace str, and the other one was res read. There's some functions I wrote a long time ago. I'm not really sure about the details of them, but they do the job, and they're quite useful for this purpose. So I hope you found that useful. So for now, that's it. Till next time. See you. Bye.